Welcome back to this course, Introduction to Cooperative Game Theory. As you might remember, we have started this introductory course with a review of non-cooperative games. There we had players and their strategies, and the idea of solving a non-cooperative game basically was that we were looking for an equilibrium where each player was playing a strategy which was his or her best response to the strategies played by the other players. The difference to the cooperative game case consists in the opportunity to have negotiations between players. And as a first solution concept for such cooperative games, we were looking at the Nash bargaining solution, which however did not include yet the possibility of coalitions among a subset of the players in such a cooperative game. And we were looking in our last lecture at some aspects fundamental to this coalition building. Based on these concepts, we will now look into a first solution concept for cooperative games with coalitions, the so-called core. And the idea is very simple. With this solution concept, we are no longer focusing on strategies, as we did in the non-cooperative case, but we are focusing on the distribution of the overall payoff amongst the individual players. And we would like to identify good such allocations, good such distributions of the payoff. And what is a good distribution? A good distribution is a distribution where each player cannot improve his individual return, his individual payoff, by joining one or more other players and form a coalition with them. So in a sense, coalitions cannot improve on this allocation. And the set of such good allocations is called the core of a cooperative game. So just to remind you where we stopped last time, we were introducing this form of coalitions for games with so-called transferable utility. And such games can be described mainly using a so-called characteristic function, which indicates a value for any coalition S, which is subset of the set of all players. And each such coalition gets assigned a certain value, and this is sufficient to characterize the whole cooperative game. The important assumption behind is that players can negotiate about coalitions, but they are also bound to their negotiation results. And this was the key difference between cooperative and non-cooperative game theory. Another important difference between cooperative and non-cooperative game theory is the focus of solution concepts. So in non-cooperative game theory, we were focusing more on strategies. We were trying to identify good strategies and then try to identify equilibria resulting from the application of these strategies. In cooperative game theory, the focus is shifted a bit. The focus is now towards so-called payoff allocations, which means towards the returns which are assigned to the players as a result of their negotiations and as a result of their coalition forming activities. So this is the basic idea now, to identify a good payoff allocation. And we define first what that means. So here we see that a payoff allocation is defined as just a vector with a component for each of the players, where the component number I, x index I, is just the payoff to player I. And remember that we have assumed that our players are rational players, and hence, of course, they try to get an allocation which maximizes the individual payoff of every player. This is the basic idea. And the question is, how can we use this concept to identify the potential or probable solution of such a cooperative game? And we will now look at two basic approaches. The idea number one is to find out which allocations are good allocations in the sense that they cannot be improved by forming coalitions or by forming other coalitions than the existing ones. And the resulting solution concept is called the core, which means an allocation which is within the core cannot be improved by additional negotiations, by additional coalition forming. The important point to notice here is that the core is a set of allocations. So it can be empty, there can be one allocation in the core, but there can also be many allocations in the core. And for sure, it's not a unique solution. And hence, in order to improve on that, there's another approach where we try to identify a payoff allocation which reflects the expected worth of a player concerning his contribution or her contribution to a coalition. And it's, in a sense, the average worth. So we have to find the average value of a player with respect to different coalitions the player can join. And this will give us a unique value, the so-called Shapley value, as a result. And this is just another way to address this problem. So we will follow these two approaches. There are a couple of more specific approaches. These are the most important ones. So let's first discuss the concept of the core. Here it is important to define first the feasibility of an allocation for a certain coalition. So we define an allocation X, such a vector of payoffs, is feasible for coalition S if and only if the sum over all vector components xi, where I runs through all the members of the coalition S, is less or equal the characteristic function of the coalition. So this means the payoff for members of the coalition does not exceed the total payoff for the entire coalition. We call this feasible for coalition S, and if you are looking at the grand coalition at N, which the coalition which comprises all players, we call this just feasible. So no longer feasible for the grand coalition, but just feasible. So this is the first definition we need. And the second definition we need is a notion of what does it mean to make the result of a game better for individual players by doing additional negotiations. So this is captured in the second definition. A coalition S can improve on an allocation X if and only if the sum of the payoffs for the members of the coalition is strictly less than the characteristic function of the coalition itself, which means there is additional money to be distributed. And now we come to the definition of the core. An allocation X is in the core of the game, in the core of this characteristic function, if and only if we distribute all the payoff available to the grand coalition, so the sum over all players of the components of the allocation vector equals the characteristic function of the grand coalition. And for all coalitions, the allocation, the sum of the allocation components for the members of this coalition is larger or equal the characteristic function of the coalition, which means we do not have this case here. For any coalition, we distribute at least larger or equal the characteristic function of this coalition to its members. So in this sense, such an allocation is feasible and not improvable. And then we call such an allocation as part of the core of the characteristic function. So in other words, if a feasible allocation X is not in the core, then there exists a coalition such that all members of the coalition could do better if they negotiate and cooperate and divide the achieved value for the coalition, the achieved value of the characteristic function of this collision among themselves. This, of course, is also in line with the minimax representation of the characteristic function we were discussing earlier, because it means that if a coalition can improve on an allocation, that the players in the coalition can improve independently of the rest of the players, independently of the outside world. Let's look now at some examples. Remember this game we discussed recently as divide the dollars and divide the $300 amongst 3 players. And we had this first example, this first version of the game, where the requirement was that all 3 players agree on a distribution, and if they do so, they get this distribution, and if they do not agree, they don't get anything. So what's the core of this example? Well, apparently, a requirement for this core is that it is Pareto efficient, so this means that all these $300 are distributed, so x1, the component of allocation vector x for the first player plus x2 plus x3 has to equal 300. And of course, all this allocation should be non-negative, but that's already everything we have to say. So any allocation vector x, 3-dimensional allocation vector, which satisfies this equation and is positive in all the 3 components, is in the core of this game. Which means there are many such allocation vectors, in fact an infinite number of these allocation vectors in the core. It just includes all Pareto efficient allocations, and in a certain sense this is symmetric in all the players. There is no difference between the components. So our version 2 of this game was a bit different, because for version 2, as you remember, it was sufficient if player 1 and player 2 agree on a distribution of the $300, and if they agree, they get this distribution. If they don't agree, they don't get it, but player 3 had nothing to say. And I leave it to you now to describe the core of this example in a similar way as a set of allocation vectors as we did here. And you will notice that this core is no longer symmetric, like the core of example 1, because player 3 plays a slightly different role. And if you manage to describe this core, then I also pose the question, what does this asymmetry mean? Can you give some interpretation of it? And then we have a third version of this game. And the third version said, well, we have to divide the $300 between any pair of 2 players. So either player 1 and 2, or player 2 and 3, or player 1 and 3. If one of these 3 groups agrees on a distribution, they get the money. Again, I leave it to you to discuss the core for this example. Observe once again, the worth of the grand coalition can be achieved by any 2 players, by any coalition consisting of 2 players. And then you could start thinking about what does this mean if any player gets a positive payoff. So assume player 1 gets a positive allocation, x1. What does this mean for the other 2 players? Could they do better? And based on this deliberation, please tell me which allocation or which allocations are hence in the core of this version, in the core of this example, if there is any. And again, what does that mean? We're now introducing another game as a new example, the so-called glove game. So you know that gloves come always in pairs, and they are only useful if you have a left glove and a right glove. So imagine the following situation. We have 2,000,001 players, and each of them can supply 1 glove, either a right one or a left one. And let's assume that 1,000,000 of the players have a left glove, and the rest, 1,000,001 players, have a right glove. So of course now you can start forming coalitions among these many players, and the worth of each coalition is the number of matched pairs of gloves. And the question is, what is the core of this game? So let's assume that any right glove supplier has a positive payoff, a positive strictly larger than 0. So remember, we have 1,000,001 right glove players. So the question is, in this case, what does this mean for the total payoff of the other 2 million colleagues? The total payoff of them, of course, will then be strictly less than 1 million. 1 million apparently is the maximum which this characteristic function can take as a value. And if one right glove supplier has a payoff larger than 0, the rest has to have a total payoff of less than this 1 million. But, of course, if these 2 million players form a coalition and exclude this one guy, they could improve of their total payoff. And this means that none of the right glove suppliers may have in the core a positive payoff. All of them have to have a payoff of 0, which on the other hand means that all of the left glove suppliers get a value of 1, which somehow reflects the fact that there is an excess in the supply of right gloves. Therefore, they are cheaper. But of course, it looks a bit strange that the difference is so big. So this example already shows us that the core is an appealing solution concept for cooperative games, but it also seems to have weaknesses. It can be empty, there can be more than one allocation within the core, and apparently, as is the case with the last example, the core does not really reflect appropriate market powers as you would expect them. And therefore, in the next lecture, we will focus on an alternative solution concept, the so-called Shapley value, which somehow improves on these aspects. Thank you very much for your attention.